Now, when we introduced irrational numbers, we showed that the square root of 2 cannot be rational because if it were, it would lead to a mathematical contradiction. But then we said, therefore, irrational numbers exist, and we define any number on the real number line that's not rational to be irrational. They fill in the gaps, as it were, on that number line. But we said nothing more about any other numbers that could be irrational. So what other numbers could we find that would also be irrational? And that's what we're going to explore now. So we're going to start with the idea of squares, which is where we first introduced an irrational number by taking the inverse of a square, which is a square root. So what I'm starting with now is the list of the first few whole numbers. And here I am including 0. I want this in here because it fits in with the pattern, so we're going to use the whole numbers. And I'm just going to start first by squaring each of the whole numbers to see what I get, come up with a new list. So I start with 0 squared, well that's just 0, and 1 squared, that's just 1, and 2 squared is 4, and 3 squared is 9, and 4 squared is 16, and 5 squared is 25, and so on. We get 36, 49, 64, 81, 100, and again, and so on. We know that will go into infinity because the whole numbers go into infinity. These are what we call the perfect squares. The idea is that I can take the square root, I can invert the square of any of these numbers, and I'm going to get back each and every whole number. So I have what's called a one-to-one relationship or correspondence between the whole numbers and the perfect squares. So then I'm left with whole numbers that are not perfect squares. Those are basically all the numbers that don't fit into this gap here. So I can create a new list. So I can think what numbers are not here that are whole numbers. Well, there's 2, and 3, and 5, and 6, and 7, and 8, and 10, 11, 12, 13, 14, 15, 17, and so on. I don't need to keep listing those out. I think we get the idea. So I know the square roots of this list give me nice whole numbers, therefore they are rational by definition. But I want to know what I can say about the square roots of numbers from this list. Well, we've already shown, first, that the square root of 2 is, in fact, irrational. That was an easy proof, known to all of the ancient civilizations that studied mathematics. Most likely the first number proven to be irrational. But what can I say about the square root of 3, or the square root of 5, or the square root of 6, or the square root of any number in this list? Well, to see what we can say about it, we're not going to do what's called a rigorous proof. I'm not going to take the time to mathematically make sure I've covered all my bases to show what I can about which of these numbers are or are not irrational. Instead, I'm going to do what's called a story proof. Story proofs are much simpler. It's where we take kind of a very basic idea, learn something about it, and then use our intuition to generalize to as many things as possible what must be true about that. That may sound complicated the way I described it, but I promise it's actually pretty easy. Though a story proof isn't rigorous, it's enough for our purposes, and I can assure you that it is in fact going to be true. So, our question is the square root of any of these non-perfect squares possibly rational? So let's go back to our definition of a rational number. When we say that a rational number is any number that can be written like this: a over b, where we say that both a and b are integers, that is positive or negative whole numbers or 0, except b cannot be 0 because we cannot divide by 0. Alright, well, we're looking here for positive square roots. We're not worried about the negative ones, so that means we can let this be a positive value. So that means a and b are either both positive or both negative. Well, it's fair enough to say let them both be positive, because if they were both negative, I could cancel out a -1 from both the numerator and the denominator anyway. So I don't lose any generality by assuming they're both positive. Additionally, I know this cannot be a whole number, because we've already found all the whole numbers as square roots by just square rooting the perfect squares. So therefore, b can't be equal to 1, because if it were, this would be a whole number. So we place another restriction on b. And finally, just like with our proof for the square root of 2 being irrational, we're going to assume that this is already fully reduced. We know that any fraction, any rational number, can be reduced to lowest terms, so let's assume a and b are already reduced to lowest terms. Because if it's not, we can just simply make that happen. It's a very easy process to reduce something to lowest terms. So assume that it's already there. So when we say that a fraction is in lowest terms, we're saying it has no common factors at all between the numerator or the denominator. But more specifically, we're saying there's no common prime factors. Now, we've sort of touched on this before, that any number can be written as a unique product of prime numbers. So let's think about this as that product. Okay? So A is going to be the product of some amount of prime numbers. I don't know how many or what they are, but I'm just going to label them as such. Let's call it P1 times P2 ... times P sub k. So I've got k prime numbers in this A here. And additionally, each of these prime numbers could be raised to some exponent other than 1. So let's call our exponents m. So let's say this is raised to the power of m sub 1, this is raised to the power of m sub 2, and this is raised to the power of m sub k, where the m's aren't necessarily unique and they could be equal to 1. So that there's really like saying no exponent there. All right, so that's my A. So then my B, since I have no common prime factors, has to be written using different primes or different p's. So let's call this p sub k plus 1 times p sub k plus 2 ... times p sub, let's just call it x. So I go from k plus 1 to x here. And also these primes could be raised to a power. So let's call this exponent m sub k plus 1, this exponent m sub k plus 2, all the way up to this exponent, let's call it m sub x. And notice that the factors here are all prime. This p stands for prime, which means there's no common prime, so there's no common factors. So this is a fully reduced rational number that is not equal to a whole number. And so we then say, I'm taking this rational number and raising it to the power of 2, or I'm squaring it. So I'm taking this whole number squared. Well, by the properties of exponents, all we do with this 2 is distribute it to every single exponent inside. And this includes down to the denominator as well. And the reason we can do this is because all that's happening inside my parentheses is multiplication and division. And so it's nice and easy the way I can make this happen here. So all I'm doing is doubling each of these exponents. Well, I'm not changing the base. I'm not changing the prime factors at all. They're the exact same prime factors. There's just twice as many of each of these p's as there was before. Well, if none of these p's would cancel with none of these p's, then nothing's going to cancel after I square it. In other words, it's going to be impossible for me to reduce the square of this fraction down to a whole number. So the square of a rational number, or more specifically the square of a fraction, has to also be a fraction. So what does that tell us? Well, if I'm taking the square root, so this final value, and I take its square root, in order for it to give me a fractional answer, I would have had to have started with a fraction. And I know that the only way it can give me a whole number answer is if it's a perfect square. So if I'm putting some number in that's not a perfect square, then my best hope for getting a rational number is that it turns into a fraction. But if that's the square root, then reversing that, squaring that fraction should get me back to one of these whole numbers, which we just showed is impossible. So therefore, I can say, without rigorously proving it, but using my intuition, that the square root of any non-perfect square must be irrational. It's impossible for it to be rational. So I didn't just show you one irrational number in the square root of 2, I showed you an infinite number of irrational numbers. Any whole number that's not a perfect square, take its square root, it must be irrational. So, the square root of any non-perfect square must be irrational. But why stop with just the exponent of 2? Why not use another exponent? Alright, well let's see what happens when we talk about cubes, or the power of 3. So again, starting with my same whole number list, I'm going to list out the first few perfect cubes by cubing each of these numbers. Well, 0 cubed is 0, and 1 cubed is 1, and 2 cubed is 8, and 3 cubed is 27, and 4 cubed is 64, and 5 cubed is 125. And I'm going to stop there, because obviously I'm getting really big really fast. But it's the idea that, again, I could go into infinity. These are perfect cubes, and if I took their cube root, then I'm going to get back to every single whole number. So again, I have the same one-to-one correspondence. So I know that the only way to take a cube root and to get one of these nice whole numbers is to take the cube root of a perfect cube. So what about non-perfect cubes? Well, I'll start that list as well. So again, it's like 2, 3, in this case 4, 5, 6, 7, skip 8, 9, and again, I'm just going to say we know that goes on. It's any whole number that's not in this list. The symbol for cube root, if you're not familiar with it, is very similar to the square root. We use that same radical sign, but right in this little crook, we put whatever root I'm taking or whatever exponent I'm inverting. In this case, I'm inverting the exponent of 3, so I write the cube root of this. So my question is, the cube root of 2 or 3 or 4 or any non-perfect cube, can that be rational? Well, it's actually very easy to show that as well because it's basically the same thing we just did with square roots. Again, my same setup. I have a over b. A over b is a fraction that is not an integer already in lowest terms. So it's got some prime factors in the numerator and different prime factors in the denominator raised to whatever exponent. And then I'm raising this whole thing now, not to the power of 2, but to the power of 3. I'm cubing it. But I'm still doing basically the same thing I did with the square exponent. I'm just distributing the 3 to every exponent inside, which means I'm just tripling these exponents. So I'm not changing the base or the prime factors in the numerator or the denominator, which means there's still nothing to cancel out. So there's no way for this to reduce down to a whole number, which means a fraction cubed must be a fraction. And so, in the same vein, if I take the cube root of any whole number, if it's a perfect cube, I will get every whole number. And so if it's a non-perfect cube, I cannot get a rational number. I can't get a fraction because reversing that, that fraction cubed must give me a fraction as well, of which these are not. These are all whole numbers, not fractions. Therefore, the cube root of any non-perfect cube must also be irrational. But why stop there? Why say squares and cubes? Why not to the power of 4 or the power of 5? The power of anything? Well, we can use this exact same argument. I can raise this to the power of anything, so let's call it the power of n. And that n gets distributed inside to each prime factor that's unique, that does not cancel out in the numerator and the denominator, which means a fraction to the nth power must be a fraction. And so the nth root of any non-perfect nth power cannot give me a fraction because taking that fraction to the nth power gives me a fraction and not a whole number. So what we've actually found is that the nth root of any non-perfect nth power must be irrational. So we have a whole horde of irrational numbers now that we can start to think about. That's pretty cool, I think. So we can take any number d, and we can take its nth root, and we say that as long as d is not a perfect nth power, then the square root of d, or excuse me, then the nth root of d cannot be an element of the rational numbers. And so that's kind of what we say here. Assuming d is not a perfect nth, then the nth, or not a perfect nth power, then the nth root of d cannot be rational, meaning it must be irrational. So irrational numbers are plentiful, and they fill in the gaps on the real number line. And in fact, although it's something we're not going to take the time to prove here because it does involve advanced calculus, it can be shown that between any two rational numbers, there must be at least one irrational number. And actually vice versa. Between any two irrational numbers, there must be at least one rational number. And it gets even crazier. When we start talking about infinity in advanced mathematics, we can actually talk about different sizes to infinity. And it turns out that from the perspective of what we might say density, there are actually more irrational numbers than there are rational numbers. So they're incredibly plentiful, yet this is just one type of irrational number, taking nth roots of non-perfect nth powers. There's plenty more out there, but they're numbers that we don't usually study, just because they don't have unique properties that carry over from number to number. But that's okay. At least we know they exist. And we can say that they're not rational, which means we can say we cannot really write them exactly. And that's what's important about them. They're not exact values. We can only approximate them. And there you have it. Irrational numbers. Remember, you watched it. You can't unwatch it.